Question 1 part 2. Estimate the gain VO1 over VI of the differential amplifier assuming that RCE of T1 is very large compared to R1. Remember to include the effect of T3, i.e. its input resistance, in your calculation. And we should end up with an answer of minus 1.87 apparently. Right, we will need some small signal model for this. So I'll draw the small signal model out and then we'll see if we can make any simplifications. And if we can, we'll work out the simplifications and then we'll try and come up with an algebraic answer for the gain. So we have an input voltage now. So we want to put a voltage in to see what the output voltage is due to that input voltage and therefore divide one by the other, ultimately to get the gain. So this is going to be T1. This is the transistor that we're driving, so this will be RBE1 and this here will be GM1 VBE1, where VBE1 is the voltage across RBE1. VBE1, there we go. And we have here RE, which goes to the reference. So this is the tail resistor, which was formerly up the top, now it lives down the bottom in the small signal model. And connected to here we have, make sure I get it right, just the R1, the input resistance of the next transistor. So this is the collector of T1, so it goes down to R1, which is our resistor that goes across the base emitter junction of T3, and we also have here the input resistance looking into T3, so this is R1, that's RBE3. For a common emitter amplifier with no degeneration, the input resistance is just the RBE. But we also have something else hanging off the emitter. So this is the emitter of the long-tailed pair, or the differential pair if you prefer. So there's another transistor which has got an RBE, and this is RBE2. And this one we connect to ground because we're driving one input to see what the gain is, looking at the output, and the output is the input of the next stage, which is the input resistance of RBE3. The other side of the differential pair we're grounding. And this too has, this is GM2 VBE2, and its collector goes straight to ground as well. And VBE2 is just that. So it would be we could work it all out on this and it would be pretty horrific. We can actually rearrange our circuit by cutting this bit out. This is T2, and T2 is connected to the emitter of T1, but everything that comes off it goes to ground, and this dependent source is only dependent upon this voltage here. So we can take all this stuff and work out a resistance value that represents it, and we'll do that first and then we'll come back to this and carry on, because this will make it much simpler for us to solve the problem. So we're going to worry about what this looks like. So I need a small signal model for just this now, and what I'm going to do is say, well, there's a voltage here, I'll call it VE, and VE is going to be driving this stage, or this transistor. So we'll just do that bit. So I've got my RBE2 my GM to VBE2. This is connected to the ground, this is connected to the ground, and I've got a voltage source here which, let's call it VS. And there'll be a current. Let's call the current, which way should we draw it? Draw it going upwards. Current flowing inwards, which is going to be IS. Now these are small signals, there's a small V and a small I. And this end here is grounded and this end here is grounded, so my VS, which is there, and my VBE, which is there, these two must be equal to each other because they're both one end of the ground and they're both connected to the emitter. So before anything serious happens, I can write out an equation that says VBE2 is equal to minus VS, where this is VBE2. Right. How will we solve this? Well, we will try to work out a resistance looking up here, and I'm going to call it RE2 because I know it's the resistance looking into the emitter of transistor number 2. And we're going to say, well, it's VS over IS is RE2, and we'll have to do nodal analysis at the emitter to figure out what RE2 is. So we'll put on here, I think this is IB2 in the answers, just make sure it's the same. Yes, it is. That's GMVB2, and that's IS, and that's VS. So we'll do a node analysis on this emitter, and we'll say that IB2 plus GMVB2 plus IS equals 0. All of these currents flow into the node. That flows into the node, that flows into the node, that flows into the node, so they all sum to 0. And we want to get VS over IS. So we'll do IB2, we'll apply Ohm's law to this resistor, and we'll say that VBE2 over RBE2 plus GM VBE2 plus IS equals 0. And we want to use our equation up here for VB in terms of VS, VB2 in terms of VS. So we'll have minus VS over RBE2 plus, or rather minus GM VS plus IS equals 0. We get the VS's on their own, which will leave us with VS brackets minus 1 over RB2 minus GM plus IS equals 0, and then we'll take the IS across. We'll do that now, be easier. Minus IS, get rid of that, done. So we'll do VS over I, so we can negate everything to get rid of the minus sign with IS, so we'll have VS brackets 1 over RB2 plus GM. Oh, GM2 actually, isn't it? Sorry. It is GM2, yes. Equals IS. So VS over IS equals 1 over, so the IS has come over that way, this has gone over there, and it's 1 over RBE2 plus GM2. Right, is that what it says on the sheet? Yes, it is. Fantastic when that happens. So this is our relationship for because this is V over I is R, Ohm's law, and this is the impedance resistance looking up into the emitter. So I can call that RE2. I'll do it there. RE2 equals. We can actually make this a bit simpler. We can make it a bit simpler. First of all, it makes a small equation, which is what we like, because if you put lots and lots of big equations together, especially if you end up multiplying their terms, the equations get enormously big and they become very unwieldy and difficult to use. And what we really want is to be able to say something about how our circuit works based on some equations. And if the equations are so big that we can't actually manipulate them sensibly, we won't be able to look at the equation and decide what it means. So a nice small equation always desirable, so wherever we can we'll try and simplify, as long as we know it won't affect the outcome of the analysis too much. We don't want to make any assumptions that actually make it wrong, but a couple of % error, not the end of the world. So we know that RBE is beta upon GM, I hope, from all on 8. So that means that 1 over RBE, any old RBE, I know it says RBE2, but any RBE really, is GM over beta. And we know that beta is almost always much, much bigger than 1. In fact, usually we assume it's 100 for calculation purposes. So 1 over RBE, which is that term there, is whatever GM is divided by approximately 100. So it's 1/100th of GM, which is this term here. So if I get rid of this term, I'll have a 1% error if beta was 100. If beta was 1,000, I'll have a 0.1% error, and so on and so forth. So actually getting rid of this term isn't such a big deal usually, because we really don't want a transistor with a low beta. Certainly not any less than 25 or so, even for a power transistor. So we can get rid of this bit here and just leave ourselves with RE2 is approximately equal to 1 upon GM2. So that's the key thing from this bit of the analysis. We can now go back and deal with our differential pair, knowing that T2, which usually I would put in as a hybrid pi transistor model, I can not have a RB and a current source for it. I can just make it look like a resistor whose value is 1 over GM2. Let's get rid of this. And we go back to our original small signal model, which was VI. We have RBE1 and GM1, VBE1, and this is connected to R1 and RBE3, which is the input resistance of T3. And then I had here before this sort of thing. Where this was RBE2 and this was GM VBE2, where VBE2 was this voltage here, VBE2, sorry. But I've just done some working out, which I've just rubbed out, that showed that all of this could be replaced by a resistance to ground. And it just so happened, and its value is 1 over GM2, and it just so happens I've already got a resistance to ground RE here, which is the real resistance that the biasing current passes through for the differential pair. So I can just tack on there in parallel RE2. And that's much nicer than having all this stuff over here. So I'll just finish off my model, and I'll delete the stuff that's dashed because we've just simplified it so that we don't have to deal with that now. And our small signal model all comes down to this, which is much more friendly. And we're still interested in VO1 as a function of VI. Now the thing that links these is VBE1, because I've got a current GM1 VBE1 flowing in this source down the board, and that must be flowing up through R1 and up through RBE3, and that's what generates VO1. So this is one circuit, or one bit of the circuit, and I know that VI must be related to VBE, because VI is impressed across RBE and across VE in parallel with RE2. So This is VBE1. VI must be linked to VBE somehow. So what I can do is I can write an equation that describes VBE in terms of VI, and I can write an equation that describes VO1 in terms of VBE1, and then I can use those two, make the VBE1 go away, and then I'll get one equation that describes the circuit. So that's what we must do now. The way we would do this is by summing the currents on the emitter node, which is this node here. So we'll have a IB1, and this is already GM1 VBE1. We'll have a VE there because we might need it in a bit, I should imagine, and we might want to describe a current here, which could go out to little IE. And we can say I've got VI and VBE1 and VE, and they're all in a loop, so VE plus VBE1 equals VI. So I can write that up quickly. I'll say that, well, I know that I'm going to need VBE, so VE is equal to VI minus VBE1. But now for the node equation properly, we'll have IB1 plus GM1 VBE1 equals IE, because IE is leaving the node and all the others coming in. We will then do Ohm's law on this, and we'll have IB1 goes to VBE upon RBE, so we'll have VBE1 over RBE1 plus GM1 VBE1 is equal to, now I've got VE here as an expression, and I've got IE. Now IE is VE upon the parallel combination of RE and big R, big E, and little RE2. So I can say that is VE over RE parallel RE2. And then I can split the VE up using this equation. So I'm going to sub in from my loop that I wrote out to get rid of VE and say it's VI minus VBE 1. And I can split this up if I want to, because it's that can go with that and that can go with that as well, and they can be two separate fractions. So I'll do that now. Yeah, I'll write it as a separate line. VBE1 over RBE1 plus GM1 VBE1 equals VI over RE parallel RE2 minus VBE1 over RE parallel RE2. Fine. Now I'm going to get all the VBE1s on the left of the equals and all the VIs on the right. So we'll have, I'll also factorise for the sake of board space. We'll have VBE1, that doesn't look very much like a BE, does it? Let's try again. VBE, that really is as good as it gets. 1 brackets 1 over RBE1, which is this term here, plus GM1, which is this term here. This term is going up there, and that minus sign is going to go away because we're essentially going to add this term to both sides. Adding it to this side will make it cancel, and adding it onto this side will make it positive. So I'll say plus 1 over RE parallel RE2, close bracket, equals VI upon RE parallel RE2, and that is this term here. Righty. Then I've just got to do my VBE1 upon VI. So VI needs to come across somehow, or something has to happen to get them into a situation where they're happy, and all this business in the bracket, will have to end up down there multiplying that term. So I'll rub out something from the top so we can carry on. Oh, I need that bracket. I'll drop-down bracket then. So we'll have VBE1 is equal to VI upon RE parallel RE2, open bracket, that's this bracket here I've just opened, 1 over RB2 plus RB1, my bad, RB1 plus GM1 plus 1 over RE parallel RE2, so bracket, which I suspect is what's in the notes. Let's have a look. Yes, it is. That's good. So if you're following in the handouts, I'm just to the left of figure 4 at the moment. So I can get rid of this bottom bit because this is my partial solution. So far we've drawn the small signal diagram. We've had T1 and T2 and the input resistance of T3. We've realised that T2 can be replaced by just a resistance to ground because the way it's hooked up, we can reduce its small signal model. We did a calculation for the reduction. We found out that its resistance, which we called RE2, was approximately 1 over GM2, and we moved it down here because it's just a resistance to ground hanging off the emitter, which is where the other transistor used to be. And then we've done a calculation which relates VBE1 to VI, just with some resistances and some conductances. Our next business is to relate VBE1 to VO1, and once we've done that, we'll be able to use the two equations to do some calculations. So this bit's actually a lot simpler than the other bit. Doesn't take near as long. We can just say that VO1 is equal to, now I'm thinking of a current flowing like that, downwards, but, or if you prefer there, these two sums of that. The only trouble is GM1 VBE1 is forcing a current round that way, which is opposite to the way I'm thinking. So a minus sign's got to come in somewhere to deal with that. So VO1 is minus GM1 VBE1 multiplied by the parallel combination of R1 and RBE3. So R1 parallel RBE3. That was quick, wasn't it? Right, so now I've got VR in terms of VBE and I've got VBE in terms of VI. If you're in the mood, you can take all this stuff here and substitute it in there and have a big equation, if you like. But you don't really need to. You can work out what VBE1 is in numbers and then substitute your numbers in if you want to. Or you can work out V out over VBE1, that's to say numbers for everything else, and then work out what VI is as a function of VBE1, numbers for everything else, and see where the important bits lie. We can actually do some simplifications here. Similarly to how we did the simplification for T2, transistor number 2 in the differential pair, where we had something along the lines of stuff and things 1 over RB2 plus GM2. And I said that this term was much smaller than that term because RBE is equal to beta upon GM, and 1 over RBE is therefore GM over beta, and since we're comparing GM and 1 over RBE2, there's a factor of beta difference. Beta's usually pretty big, so this one is the smaller one, we can just get rid of it. Well, the same thing is true just here. We've got a 1 over RBE1 and a GM1, so this term goes away with only a small error. Similarly, it transpires that RE2 is much, much smaller than big R big E. And if you look at the question again, RE big R big E is 150 kiloohms. RE2 depends on the exact values you use for the temperature. So RE2 is 1 over GM2, which itself is, so GM2 is EIC2 over KT. If we assume that KT is 0. What does it say in here? So I derive the same numbers. KT is 0.026. I'm not sure what temperature that's worked out for, but it'll be about room temperature, almost certainly. Or is that KT over anyway? If you prefer, you can say 1.6 E minus 19, 1.38 E minus 23, 300 Kelvin or so. Anyway, if you sub in some sensible numbers, we know what IC2 is because we worked it out in part I of this question, and I think it came out to be about 35.3 microamps or something like that. So you pop that in there along with the electron charge, Boltzmann's constant and the temperature, and what comes out is in the order of 750 ohms or so. In fact, did I work it out earlier? No, I didn't. I didn't write it down anyway. Now, RE is 150 kiloohms, RE2 750 ohms, assume you did the 1 over at some point. Obviously this is much, much smaller and it dominates. So what we can also do is get rid of the RE term from there and the RE term from there. So our expression then simplifies down to VI upon RE2 brackets GM1 plus 1 over RE2, those brackets, is equal to VBE1. And we still need to use this bit here. You can work out, if you want, what RBE3 is and compare it with R1 and see if you can actually neglect R1 or RBE3. Chances are it will be R1 that you're hoping to neglect. In fact, the next few parts of the question deal with that. Yes, the next part, II and so forth, deal with that, or part 3 rather. So, what can we do in terms of numbers? If I clear off some of this stuff, we can put in some numbers and see where we get to. So we had RE was 150 kiloohms. We have R1 is 14 kiloohms. We've got GM1 is EIC on KT, which is 60 microamps, calculated in part 1, divided by 0.026. So that must be KT over E then, or some such, E over KT rather, which is apparently 0.023 volts per amps per volt, or if you prefer Siemens or Mohs. Similarly, RBE1 is equal to beta 1 over GM1. We'll be taking beta 1 as 100, so that will be 100 divided by 0.00. Really? Oh, missed a 0, that's terrible. 0.0023. Yes, that makes sense. We could do that something smaller. Yeah, possibly. 0.023, which leaves us with 43.5 kiloohms. All these little calculations for RB and beta and so forth are in EEE225. Now, if you're not clear on how they come to be, go back into the notes or watch the videos for the transistor amplifier lectures, which I think starts at lecture 12 or thereabouts, for EEE225. Then we have RE2. and that's KT over EEE2. So we've done the 1 over GM is already in here, which is why this has been flipped. And that leaves us with 0.026 upon 35.3 microamps, which is 737. So when I said 750 earlier, I was on the money, more or less. And RBE3, which is beta 3, which we would call 100, over GM3. And we can work out what GM3 is from knowing that T3's collector current is a milliamp, which we calculated in part 1 as well. So that will be apparently 2.6 kiloohms. I'm not working these out because these are the numbers that are given on the solution. If you make slightly different assumptions about the temperature, you will end up with slightly different numbers. Doesn't mean that numbers you've got are wrong, but I want to give you one consistent set. So I'm going to use the same ones that are on the sheet. Right, so then you've got to, having got all your numbers together, which is that one, tell you what, I'll do it in a different colour. That one, that one, that one. Oh, that one I never did. RBE1, oh, 43 I did. That's the GM1, that one, that one. You'd use the two equations that you derived, which are VB1 is equal to VI over RE2. This is the reduced version. GM1 plus 1 over RE2. And you just sub in for VI a kilovolt. It's easy just to have a 1 there. And for the output part, we'd have actually VO1. VO1 is equal to minus GM1 VBE1 times R1 parallel RBE3. Sub in your numbers. It's just a numerical exercise by this point. Everything that is in these equations is here, and it ought to give you, for this chunk, VB1 is equal to, what was it say, 0.371 apparently. I'm not going to put in the numbers, but I 1 there, that's 737, that's 0.0023, that's 1 over 737, and you just pop it in your calculator. Having got it, you can put it in there. That's 0.0023. This lot you'd have to do, and you'd have R1 times RBE3 over R1 plus RBE3, because it's a parallel combination. Where R1 is 14K, RBE3 is 2.6K. Now, if this was much smaller than the 14K, so we won't worry about R1, we'll just call it RBE3. As it is, they're less than an order of magnitude apart, so we'll probably have to consider them both, I would have thought. This will yield about a 10% reduction in that, or thereabouts. Slightly more than that, actually. Same for the bottom, sub it in and you get VO1 as a function of VBE. And if you do that, then you should end up with minus 5.04. And then you would combine that number and that number together in terms of subbing this into this equation here. And the total answer minus 1.87, or thereabouts. As I say, the exact numbers aren't really of any consequence. It's the question of how you arrive at the solution. It's the method that's key. Right.